Welcome everybody. Welcome everybody. Okay, so this week we're gonna continue our construction of the number systems. So last week we developed the natural numbers, and we developed something that looks like the natural numbers, behaves like the natural numbers, smells like the natural numbers. So to all purposes, we pretty much define something that is the natural numbers. What we have is the natural numbers. And now we need to continue on, and the next step is the integers. So in this video, we're gonna see how we build the integer numbers from the natural numbers that we already have. So the natural numbers, we're good with them. So we're gonna assume we have everything and we know everything we need to know about them and move on to the integers. So how do we define the integers? Well, the integers is the natural numbers and the negative natural numbers. I want to define it in a way using equivalence relations, because that's going to help us also understand the next step, which we're going to use in the rationals. So here's what we're going to do. So we're going to define this equivalence relation right here, the little tilde, this little thing, and it's going to be a relation on omega 2 times omega. That means, as a relation, where does this leave? Sim is a subset of omega times omega times omega times omega, right? So it's a set of pairs, and the pairs, each element of the pair comes from omega times omega. And we say that AB is related to CD if this happens. A plus the last one plus D equals B plus C. Okay. And then we're going to define Z, which is the set of integers, to be the quotient under this equivalence relation. So we're going to take all the pairs and we quotient under this equivalence relation. Go back to the equivalence relations video if you don't remember exactly what that is. But essentially, when we're doing this, we're saying, well, all the pairs that are equivalent, we want to make them to be the same. We want to identify all pairs that are equivalent, and now we obtain this quotient where the things that used to be equivalent now are the same, that equal. On the quotient, things that used to be equivalent become equal. The quotient is a set of all equivalence classes. Let's see how these guys look like. So if omega looks like, let's write it down, 0, 1, 2, 3, that's omega. And then you have omega times omega. You have like a grid, right? And that goes on, and it goes up. That's omega times omega. And then this one is 0, 0, and this one is 1, 0. This one is 2, 0, and here is 0, 1, and here is 1, 1, and here is 2, 1, 0, 2, right, so on and so forth. We have this grid of elements representing the Cartesian product omega times omega, who's equivalent to whom. Okay, so let's look at, I don't know, let's look at this guy, 0, 1. Who's equivalent to 0, 1? Well, 0, 1 is equivalent to, for instance, 1, 2. Yes, if you look at the definition, you get that 0 plus 2 equals 1 plus 1. Right, that checks. Yeah, so it's equivalent to that one. So 1, 2 is right here. 0, 1 is also equivalent to, let's say, 2, 3, right? Because 0 plus 3 equals 1 plus 2. Check. That one is right here. And it's also going to be equivalent to 3, 4, this one up here. So all these guys are equivalent to each other. If you look at, let's say, 2, 2, 2, 2 is going to be equivalent to this one that is up here, that is, this one is 3, 1. And equivalent to that one. 0, 0 is going to be equivalent to 1, 1. It's going to be equivalent to 2, 2. All of these are equivalent. All of these are equivalent. Right? And all these lines are the equivalence relations. So each equivalence relation corresponds to one of these diagonals. Yeah? So do they look like the integers at all? Well, if you think of them, they have kind of like a direction, like it goes like the natural numbers, right? That's where the natural numbers go when you add 1. But then you have the negative direction. Yeah, so essentially you have lines going one way and going the other way, and then like if you look essentially like, well, the diagonal that way, or I can't know. Well, you get that the integers, right? And then we're gonna want essentially this element here, this line up here to represent 0, this one up here to represent 1, this one 2, this one 3, and then this one is gonna be -1, -2, -3, -4, and then, well, you have lines that go in both directions, so we're gonna end up with all the integers. Essentially, what's going on, and this is a secret, is that a comma b represents the integer a minus b. Why did I say it's a secret? It's the thing is that we don't have a minus. We all we have so far is the natural numbers. The natural numbers are only positive. We don't have negative numbers, right? Remember the natural numbers, each natural number n is defined as a set of all the previous elements, and those previous elements were the set of the previous elements, and we get these weird natural numbers. We don't have anything for the negative things. This is only, we start from 0 and we start building up. Nothing for the negative things. We know how to add natural numbers. We would find that last time by recursion. And this sum right here, this sum here, it represents to the sum of the natural numbers, right? Because this, and the natural numbers, we use omega to represent the natural numbers, right? So this is addition on the natural numbers that we are using in the definition of the equivalence to define the integers. So, but we cannot consider negative natural numbers. So then this thing up here is not something that exists yet. I mean, it's not too hard to define it, but essentially that's what we're doing. We are defining the integers. So we are kind of talking about these negative guys right now. So that's why I say it's a secret. What I mean is that inside the theory, this doesn't exist. Inside the theory, all that exists is the pair a comma b, and we humans think of it as a minus b, because that's what's going to be at the end. But we don't have a minus b. All we have is pair a comma b. And then there are going to be different pairs, like 0 minus 1 represents -1, and 1, 2 represents also -1, right? Okay, so that's how we represent the integers. Then now let's look at who are the obvious, the usual suspects. So who is the 0 of the integers? Well, it should be the pair 0, 0. By the way, these guys here are paired. This is the pair that we defined also in the previous one, right? By the way, so this is essentially this guy. Recall that AB means AB. Yeah, so that's why we made the pair. So 0, 0, which should be what's representing the 0 of the integers, but it's not just the pair 0, 0. It's the whole equivalence class, because remember, we are considering Z is its quotient, right? So the notation, this bracket here, if you read the textbook, this means the equivalence class. This is a set of all the y's that belong to the domain of the equivalence class, in this case omega cross omega, such that y is equivalent to x. So that's what the bracket means. So this is the whole equivalence class. And then these 0 here are these zeros. We are using 0 to define 0. No, these zeros that are here, these are the zeros of the natural numbers, right? So this is essentially what we mean here is the class of the pair empty set, empty set. Remember that the empty set is the one that represents the 0 of the natural numbers. Yeah? Yeah, so 0 of the natural numbers, omega, remember, is the natural numbers, is just the empty set. And this is, essentially, this is the equivalence class. And if you want, you can decode that. That's the pair is that set that contains this and contains this, which is the same as the equivalence class of the set empty set. Okay, and if you actually want to see exactly what this 0 is, what the 0 of the integer is, 0 of the integers is the whole equivalence class. So this is actually the whole set that contains the pair 0, 0, but it also contains the pair 1, 1 is equivalent to it, and also contains the pair 2, 2 is equivalent to it, and all the ones that are n, those are all equivalent to 0, 0. So that's the equivalence class, and each of them is a pair of natural numbers. So this guy up here is what we're using to represent the 0 of the integers. It's a bit different than the 0 of the natural numbers. That was very simple. But okay, well, is what we use. What about 1? 1 is going to be the equivalence class of the pair 1, 0. And again, let me just emphasize, this is the 1 of the natural numbers and the 0 of the natural number, right? Because remember we say that we are thinking of 1 minus 0 when we think of this pair. And again, this is a whole equivalence class of pairs. This is a big set, but that's what it represents. That. Okay, good. What about, we need to define addition, multiplication, order. We need the basic operations of the integers to be able to call these guys the integers. They need to, as we did before, they need to look like and behave like the integers. So to make them behave like the integers, we need to know how to add them. How do you add them? Let's do it on a side. Remember, this is the part that it's not part of the theory, but it's on our intuition. We are thinking of a comma b as representing the element a minus b, and we are thinking of c comma d as representing the pair c minus d, right? So the addition should represent, if you add these two, you're gonna get a minus b plus c minus d. And how do you represent that number? Well, these guys a, b, c, and d are all natural numbers. They're all non-negative, and then here we have some negatives and some positives. So what we need to do is rearrange this and say, well, this is the same as a plus c, that we know is positive, minus b plus d, that we know is positive. Yes, so now we're going to represent this guy with the pair a plus c, comma b plus d, because we know these guys are positive, and the pair that this represents, that's the one we want. So we're going to take a first two coordinates, a plus c, and form the pair with adding the last two coordinates, b plus d. And then we get the equivalence class of that. Because remember, all the integers are equivalence classes. Okay, so that's intuition, and that's how we define it. Can we do that? We can do that, but to do it, we need to be careful. We need to lemma that says that this is well defined, right? Whenever you define something on equivalence classes, you first need to know that it's well defined. And what does it mean? Remember, we said that in the video of equivalence classes, but what does it mean? What does it mean when we say that something, you need to prove that something is well defined? Well, suppose that you have that a comma b is equivalent to a prime comma b prime, and c comma d is equivalent to c prime comma d prime. Yeah, so that means that the equivalence classes of this guy and this guy are the same equivalence class, and the equivalence class of this guy and this guy are the same equivalence class. So that means if we add these two, or if we add these two, we need to get the same thing. Otherwise, this definition doesn't work, right? For this definition to work, here we took a comma b is one representative for the equivalence class, but we could have taken a prime b prime. And here we took cd, but we could have taken c prime d prime. They are both in the same equivalence class. So we need to know that this implies that a plus c comma b plus d is equivalent to a prime plus c prime. Okay, so that's what it means to say that this operation is well defined. Yes, and this requires a little proof. It's just a two-line proof, but let's do it. Let's do this two-line proof to show that this operation is well defined. Well, so what do we know? We know that AB is equivalent to A prime plus B prime. So we know that A plus B prime is equal to A prime plus B. That's from the first thing that we know. And then we also know that C plus D prime is equal to C prime plus D. This is what we get from this assumption right here. Cool. So what can we do now? Well, okay, let's see what we want. We want to show that those two things are equivalent. So that means that we want to show that A plus C plus B prime plus D prime equals B plus D plus A prime plus C prime. Yeah? Do we get that? Yeah, so adding these equations right here, if we add these two equations, we get exactly what we want, right? We get A plus B prime plus C plus D prime equals A prime plus B plus C prime plus D. Right? I just added these two right here. We got this. I'm missing, no, that's fine. Let me just fix that. Let's see. And now we see that this thing that we got is exactly what we want arranged in the terms. Okay, so if we start from pairs that are equivalent doing this operation, we end up with pairs that are equivalent doing the same operation, and that's what allows us to define this operation on equivalence classes. So whenever you have an equivalence class for AB, doesn't matter if you take AB or anything equivalent. Here it doesn't matter if you take CD or anything equivalent. We always end up with something equivalent to the sum. Cool. So that's what we need to be able to define the sum. Now, next step is multiplication. What's multiplication? Well, again, we can do it. We can just look at it on the little side and see what it should be. So we know that AB is trying to mean A minus B, and CD should mean C minus D, right? So if we multiply these two, what are we gonna get? We're gonna get AC minus AD minus BC plus BD. Correct? And again, so some of these terms seem to be negative, some positive, but in our pairs, we always have positive elements on both sides. So we need to arrange them, and the way we arrange them is this is A is equal AC plus BD, that's positive, because those are all positive, minus AD plus BC. Now, and those are all positive. So now we have one positive term and another positive term. So that's our guy. So we're gonna get AC plus BD on one side of the pair, on the other side AD plus BC. And that's our pair, and then we take the equivalence class of that. And again, if you want to make this definition on equivalence classes, we need to check that it's well defined. Okay, so the same as we did before, we need to check that if you take different representatives of the same equivalence class and you multiply them together using this operation, you're going to get things that are equivalent, right? So I just copy and paste the beginning of last lemma. So this operation is well defined on equivalence classes. That means that if you start with two things, that A and B is equivalent to A prime B prime, and CD is equivalent to CD prime, then you need to get from here that the images are equivalent. Okay, so that you need to get from here, and it's this whole mess, you need to get that AC plus BD plus A prime D prime plus B prime C prime is equal to A prime C prime plus B prime D prime plus AD plus BC. Okay, so what I'm saying here is that those are equivalent, that images are equivalent. And if you get that the images are equivalent, then you can define these on equivalence relations. And to check that's the case, well, I'm gonna let you guys try that one at home. Essentially, you need to do the same as the previous one. You just put that what do we know, and then you need to manipulate what you know. Not like this one, is a bit more complicated. And the best way to do that is just to figure out what you want and exactly see what you need so you can manipulate it. Try it out. Okay, so we got multiplication. Now we want order. Okay, so one thing to mention again, let me just repeat. Here, this operation of multiplication, I can do it here. This multiplication and this plus and this multiplication and this multiplication, this plus that we use to define multiplication of the integers, these are all on omega, right? These are all on the natural numbers. So these are all, we are using the multiplication and addition of the natural numbers that we know from last week to define it on the integers. What about ordering? The ordering is going to be defined as follows. So we're going to say that AB is less than that if A plus D is less than, in the natural numbers, to B plus C, right? And again, if you think of AB as A minus B is less than C minus D, if and only if A plus D less than B plus C. That's where that comes from. Yeah? Okay, so those definitions come from there, from our intuition of what they should behave. But then, again, so that's our intuitions of what the integers should be. But we don't have, again, we don't have this minus sign. So this intuition is not based on something intrinsic to the theory. So if we don't have this intuition and we're just defining these operations completely abstractly, how do we know that they do what we want them to do without just going to our intuition? Well, this is all we need to do. We need to show that the integers behave, or this set with these operations, this crazy set with these crazy operations, behaves the way the integers behave. And then once we know that, we can treat these guys as we always treated the integers in our other math classes. And the way to do that is to show that, in this case, there is an order commutative ring. So a ring, you guys learn in algebra what that is. I mean, you need a bunch of properties. I don't know if you remember the properties. Multiplication and addition have to be commutative, associative. You need distributivity of addition over multiplication. You need a 0, that if you add anything by it, you get the same thing. You need a 1, that is identity for multiplication. And the order means that if you have positive things and you multiply them, you stay positive. All those basic properties about plus, times, and less than, you need to show that they work, right? And once you show those properties, then now you have a structure that looks exactly like the natural numbers, like the integers. So you might as well treat these guys as the integers. There is one thing you might say, and it's, okay, so we have the integers, but we have remember 0 is this super weird guy, it's this big set equivalence class of things. While the 0 of the naturals, it's just the empty set. And usually in math, 0 of the naturals, 0 of the reals are the same object. So what we do here is think of an embedding. So we're gonna put the natural numbers inside the integers. And how do we do it? Well, the number n, where should the number n go? Well, it should go to the pair n comma 0. Right? And then this is the pair, and of course, this is the equivalence class corresponding to the pair. Okay, so we have a map from the natural numbers to the integers. And what do we need to be true about this map? Well, we need it to be a homomorphism. What does it mean? It means it preserves the operation, right? So it means that if you do E of n plus m is the same as E of n, it means that if you do E of n plus this omega m, we should get the same thing as E of n plus E of m, where this plus up here is the plus of the integer numbers in the image, and this plus up here is the plus on the natural numbers. So E maps one plus to the other plus, and the same thing with operations of multiplication, and the same thing with the ordering relation. And of course the 0 goes to 0 and the 1 goes to the 1. So this is what it means to be a homomorphism. It's an embedding, it preserves all the structure of the natural numbers, stays the same inside the integers. And once you prove this, now we can say that what we have is something that is really like the integers. And if we want, we can think of the natural numbers as being a subset because we have now this embedding inside. This theorem over there, each step is just a little proof, because probably each step has a line to prove commutativity, associativity. Each one requires a little proof, and the proof uses the fact that we already know that the natural numbers satisfy the properties that we mentioned last week of commutativity, associativity, and we had some properties of the natural numbers over there, and now we can use them right here to prove these guys. Alright, so next video we'll start with the rationals. See you next video.